today we will see a special kind of a diode, that is a Zener diode. So before we actually look into the Zener diode, we will just have a look at the concept that we have already studied, that is junction breakdown. You know, whenever a PN junction diode is reverse biased, what happens? Only a very small current will flow through it, and that current is a constant current. It becomes constant after reaching a certain value, right? So that constant amount of reverse current that flows through a reverse biased diode is called the reverse saturation current. This is the reverse characteristic of a diode. This is voltage axis, this is current axis, VR and IR. So that reverse saturation current is IS, as shown here. It will become constant after it reaches a certain value. So if you increase the reverse voltage beyond a particular value, that is called a breakdown voltage, then the junction will break down and a large reverse current will flow, right? A large reverse current will flow in the reverse direction, right? That happens when you increase the reverse voltage beyond the breakdown voltage. So what you can do is, if you are going to use a resistance in series with the reverse biased diode, see, this is the diode D1, it is reverse biased. The positive terminal of the battery is connected to N side of this diode, and negative terminal of the battery is connected to the P side of the diode. So it is reverse biased. It has a voltage of VR, reverse voltage across it, right? So then there is the current IR. If you use a resistance R1 in series with that diode, then the power dissipation, it can be kept at a particular level which will not destroy the device. Each diode will have certain rating, as we have seen. Maximum power rating of a diode will be specified while you buy it, or it will be there in its data sheet. So if you try to limit that power dissipation within its maximum level, then the diode can be kept safe from getting damaged, right? So in this case, the diode may be operated continuously in the reverse breakdown. Continuously in the reverse breakdown means in this particular region, without causing damage. If the power, if it does not exceed the maximum power rating, then you can keep operating diode in its reverse breakdown region. That is by using a resistance in series with the diode, that resistance will limit the current, thereby it will limit the power dissipation. The reverse current, it will return to its normal level when the voltage is reduced from the reverse breakdown level. See, if it is operating in this level, in the safe region, then if you bring down the voltage from the reverse breakdown voltage, then again it will start, again the current will go back to its normal reverse saturation level, right? So for that, you have to be very careful that the resistance, it has to limit the current within the maximum level, and thereby the power dissipation is also limited, so that the diode does not get spoiled. So before we go into Zener diode, we will see what are the different breakdown mechanisms that can happen in a PN junction. So there are actually two types of breakdowns that can happen. One is Zener breakdown, the other one is avalanche breakdown. So Zener breakdown it normally happens when the reverse bias voltage is less than 5 volts. When the reverse voltage applied to the PN junction is less than 5 volts. When the depletion region is very narrow, so initially it will be narrow, right? Depletion region, it will be narrow. Then if you apply the reverse bias voltage, then there will be an electric field strength produced. Electric field strength means voltage appearing per width in volts per meters, right? The strength of the electric field will be very high. If the depletion region is narrow, the strength of the electric field, that strength of the electric field means voltage per meter, per length. If it is narrow, the strength of the electric field will be very high. Because of this high strength or high intensity electric field, the electrons, they gain strength and they break away from their respective atoms. Because of the electric field, electrons are the valence band electrons, they are removed away from their atoms. Thereby, if the electrons are removed away from their atoms, they will become free electrons. So once there are free electrons, they will start conducting, right? So the depletion region is basically an insulating material. There are no charge carriers. That's why we call it a depletion region. It is depleted of charge carriers. But if you subject that thing to a very high strength electric field, it will cause the electrons to break away from the atoms, and they will become free electrons, and it will start conducting. So this is called ionization by electric field. Here ions are produced because of the electric field that is applied, and the mechanism or the breakdown is called Zener breakdown. Okay, this normally happens when the voltage is less than 5 volts, right? Now, this we said when the depletion region is narrow. Now, if the depletion region is not that narrow, if it is wide, if the depletion region is too wide, then what happens? The electric field strength will not be so high for the electrons to break away from the atoms. Then, in such cases, you have to give sufficient energy. The electrons in the reverse saturation current, they can be given sufficient energy. So these electrons, when they are given energy, they will strike the atoms within the depletion region. They will go and strike the neighboring atoms around them. So when they strike the atoms, the valence band electrons are broken away. I mean, they are broken free, right? The valence band electrons, they break free. These electrons which are released in this way, you know, the electrons are, first of all, they are released because the other electrons come and strike their atoms. When the electrons come and strike their atoms, the atoms will release the outer electrons, valence band electrons. So those electrons which are released, they again collide with other atoms, right? So electrons, they are released because of collision. Those electrons, they again collide with other atoms to produce more and more free electrons. That is called an avalanche effect. Okay, avalanche effect means electrons hitting an atom, releasing more electrons. Those electrons again hitting a particular more and more atoms, so that they can release more and more electrons. This is called ionization by collision. Ionization by collision. Here, the ionization happens due to the collision. That's why it's called ionization by collision. And the breakdown is called avalanche breakdown. And this normally happens when reverse bias voltage is above 5 volts. That is, you have to give sufficient energy to the electrons to break away or to go and strike the other atoms. That's why the reverse bias voltage is more than 5 volts. So regardless of which breakdown it is, Zener breakdown or avalanche breakdown, so normally the diodes which are used in breakdown region are called Zener diode. So what is a Zener diode? It is a diode which is designed specially for operation in reverse breakdown region. So we operate this Zener diode in the reverse bias, that too in the breakdown region. So they are also called breakdown diodes. So what is the speciality of this Zener diodes is, so we make use of this particular region where, you know, it can be safely operated if you keep it below that maximum permissible level. Okay, so this they have a breakdown voltage that remains extremely stable. That breakdown voltage will be stable. That will be constant over a wide range of current levels. So even if you change the current, the voltage will remain constant, right? So this property of Zener diodes is used, or it is utilized in applications like voltage reference source. Voltage reference source means a power supply, a DC power supply, where you need to get a very fixed DC voltage. It cannot change. So if you use a Zener diode in its reverse bias, in its breakdown region, it will have a constant voltage across it. So that can be used as a DC power supply, right? That's the logic of having a Zener diode voltage regulator. So this is a symbol of a Zener diode. So a normal diode is just an arrow mark with a vertical line. Here to that vertical, like a Z here, Z, right? So this indicates it is a Zener diode. And the Zener diode is operated in reverse bias. So P side should always be connected to negative of the battery, negative terminal, and the N side, cathode, should be connected to positive. And the reverse current is Zener current IZ. This is called Zener current IZ. Okay, this is a symbol of a Zener diode with the polarities of how it should be connected and the direction of the current. Right? So to the normal diode, if we show two lines like this, like a Z, that's a Zener diode. And these are the characteristics of Zener diode. So forward characteristic will be the same as, you know, a normal diode, whereas in the reverse characteristic, you can see it's a vertical line. The vertical line in after breakdown, that's called VZ is the Zener breakdown voltage, and this vertical line is in the voltage is maintained. A constant voltage is maintained when it breaks down. So that property we are using as a voltage regulator. So here IZK is the reverse current near the knee of the characteristic. This is a knee where it starts rising. That is the reverse current near the knee of the characteristic. And IZM is the maximum Zener current that can be allowed that is limited by maximum power dissipation. That means if power dissipation goes beyond a certain value, diode will get spoiled, it gets burnt, right? For that particular power, what is the current? That is maximum Zener current. Then there is a very, very small rate of change of voltage, delta VZ and delta IZ. Change in the current, change in the voltage. To measure the impedance, we will use that. Then IZT is some test current for measuring VZ at a particular value. We will take test current and find change in the voltage and change in the current. Right? This is the reverse characteristics or typical characteristics of a Zener diode and some of the parameters. VZ is Zener breakdown voltage. IZK is reverse current near the knee. IZM is maximum Zener, and IZT is test current. Some random value that we choose. And the dynamic impedance or the impedance, that's called dynamic impedance, we indicate by Z. The Z subscript indicates it is Zener impedance. Z for impedance, subscript Z for Zener impedance. That is change in the voltage divided by change in the current. Okay, it takes some test current. For that, find change in the voltage and change in the current. That will be very, very low, because change in the voltage will be very low in case of a Zener diode. It's almost constant, so dynamic impedance will be very small, near to 0. Then the power dissipation is given by PD, power dissipated, that is voltage into current. We take the maximum current into consideration. IZM stands for maximum current. VZ is the Zener voltage, Zener breakdown voltage. Okay, so in a Zener diode, that VZ is a fixed value, it's a constant value. So while you choose a particular diode for any application, in that application, for example, you might be asked to design a voltage regulator, say for 5 volts. If you want to get a 5 volt constant DC power supply, then you have to choose a Zener diode which has a breakdown voltage of 5 volts. Because in that breakdown voltage, or at that breakdown, that Zener diode will maintain a constant voltage drop of 5 volts across it. So that can be used as a voltage reference source for your DC devices. Right? So then if you consider the equivalent circuits, the DC equivalent circuits is in its reverse bias, it will have a constant voltage. You can draw an equivalent of it with the DC power source or DC voltage source, that is VZ. Just like you have drawn for a forward bias diode, it was VF, right? It will have a constant voltage drop across it in the forward direction. Here it is the reverse voltage of VZ. The Zener diode can be replaced with VZ. If you consider AC equivalent circuit for changing values of currents and voltage, you can consider constant VZ, then impedance, Zener impedance ZZ, Zener impedance ZZ in series with it. So that will make up for the changes that you might find in the values of voltages and currents. These are the equivalent circuits. So you can take one example, a numerical example involving Zener diode. So a 4.3 volt Zener diode is connected in series with a 820 ohm resistor and DC supply voltage of 12 volts. You are asked to find the diode current and the power dissipation. So what is given? It is given that a 4.3 volt Zener diode. So when you write the specifications of Zener diode, we mention voltage. That voltage is the Zener voltage. That is actually its breakdown voltage, right? So that means VZ is equal to 4.3 volts. Let's write the given things. VZ is equal to 4.3 volts. It is connected with the series resistor. The resistance value is 820 ohms. You can take that as R1, that is equal to 820 ohms. And a DC supply voltage, you can take E, that is 12 volts. You are asked to find the diode current and power dissipation. The circuit diagram is not given, but based on the things that are given, you can draw the circuit. You can draw the circuit like this. Similar to what you have seen in the first part, that is, there it would be forward bias. But since here it is Zener diode, we have to connect that in reverse bias. See, the Zener diode has to be connected in reverse bias. So this is positive is connected to N side, negative is connected to P side of the diode. Right? It is reverse biased with the reverse voltage of 4.3 volts across it. Then the supply voltage is given as 12 volts and resistance in series it is given as 820 ohms. Right? It is given as 820 ohms. You are asked to find the value of IZ. You are asked to find the value of IZ. So how to find that? just use KVL. If you use KVL, what do you get? E will be equal to voltage drop across R plus voltage drop across VZ, right? What is voltage drop across R? IZ into R plus VZ. So E will be equal to IZ into R, voltage drop across this R, current into resistance, IZ into R, plus VZ, voltage across the Zener diode. So we want the current, right? If you rearrange this, I can write the equation for current IZ will be equal to E minus VZ divided by R. E minus VZ divided by R. Now you know all these values, just substitute them. E is 12 minus VZ is 4.3 divided by R. R is 820 ohms. You substitute, what do you get? Calculate. 12 minus 4.3 divided by 820. 9.39 milliamps. Yes, exactly right. So Zener current or the diode current is 9.39 milliamps. Right. It's in the reverse direction. In the diode, it's the reverse current. The Zener current, you call it 9.39 milliamps. You are also asked to find the power dissipation. What is the power dissipated? Power dissipated, or the power dissipation, you can say PZ. You can write it as VZ into IZ. What is VZ? 4.3. IZ is 9.39. So what is it? If you multiply, you might get this 40.37 milliwatts. Right? 40.377 milliwatts. Do you get the same? Okay. That's just an example of how the Zener diode can be connected in a circuit and find the power dissipate. Right? Next, we have said that because of the Zener diode's property to have a very constant reverse breakdown voltage, we can use them as a voltage regulator. But what are these voltage regulators? So voltage regulator, it's a circuit which takes unregulated DC as input and provides a constant DC output voltage, irrespective of changes in the line voltage and the load current. So what do you mean by unregulated DC? Unregulated DC as the input means, see, in a rectifier, you have obtained a DC, right? You have obtained pulsating DC first, then you have applied a filter, then you have obtained something. So in that filtered output also, there are some ripples, you can see, right? There are some ripples, there are some changes. The peak-to-peak ripple voltage was there, right? That you have seen. So, and that voltage, again, it changes if the load current changes or if the line voltage means the source voltage changes, then also the output will change. The output of a full wave rectifier with a filter may be called unregulated DC because it varies with changes in the load current as well as the line voltage. But when you are going to use that as a power supply for any electronic circuits which require a stable DC voltage, it will not be suitable because it will not tolerate that much changes in the supply voltage. The appliances or devices which require DC source, they expect a constant voltage as the input, right? That's why it is necessary to regulate the output of full wave rectifier with filter. So where do this regulator come? Actually, it is after the full wave rectifier with a filter, you are going to regulate it. So normally, for AC to DC conversion, you will be starting from an AC, then you are having a step down transformer, then you are having a rectifier, then a filter, and after that you have to use this regulator circuit. Okay, then whatever you are getting is a constant DC output voltage. So that will be treated as a power supply. Okay, so this is the block diagram of a regulated DC power supply. So Zener diode can be used as a voltage regulator because they have a breakdown voltage that remains extremely stable or constant over a wide range of current lengths, right? Because that means even if you change the current, even if the current changes or the line voltage changes, the breakdown voltage remains constant for a wide range. So now when you use these Zener diodes as voltage regulators, there are two kinds of circuits. one is regulator with a load and the other one is regulator without a load. That means you can connect the load in parallel with the Zener diode and use it. Otherwise, you can just use Zener diode and directly to the Zener, from the Zener diode, you can extract the voltage references. So we will see them one by one. First, we will see regulator with no load. So this is an example for a regulator circuit without a load connected. So output voltage is measured across the Zener diode directly, right? It does not have a load and is normally used as voltage reference source where the current requirements are very low. It supplies only a very low current, and that current is much lower than Iz to the output. Okay, so here there is an input voltage. This input voltage will normally be a variable voltage, right? It will be a variable voltage. So a variable voltage means it will change, the values will change. So even if this value changes, the output voltage has to remain the same. Output voltage has to remain the same. Output voltage has to remain the same means then what is the output voltage? The output voltage is the Zener breakdown voltage. So that Zener breakdown voltage remains the same, right? So if the voltage changes, here resistance is constant. If this voltage has to remain the same, what should change? There is only one parameter that can change to keep this voltage constant, that is Iz. So Iz will change so that the output voltage will remain constant, right? Here from this circuit, you can write Iz equation as Iz is Vin minus Vz divided by R, right? Vin minus Vz divided by R1. Take R1, you write R1. Take R, you can write R. Anyway, it's so here we have taken R1. So Iz is equal to Vin minus Vz divided by R1. So if input voltage changes and Vz has to be constant, right? And R is constant, then Iz will change depending on the value of the input voltage. So similarly, you can find the equation of the resistance of that is used here by changing this. R1 will be equal to Vin minus Vz divided by Iz, right? This is the way you can connect a Zener diode directly as a voltage reference source without using a load. So there is another example of a circuit or another kind of a circuit where you can use a Zener diode along with the load resistance. This is a regulator with a load. It's also called a loaded regulator. So here a load resistance is connected in parallel with the Zener diode. You can see the same circuit, but along with the Zener diode, there is a load resistance RL, right? The input is again, it's a variable input. That means small changes can happen in the input. So this input is actually the output of that rectifier, or it could be any unregulated input, unregulated DC input voltage. But what you get at the end is a regulated DC output. Fine. What you can see here is at this particular node, the current entering is IR. The current entering is IR, and from here it takes two paths. One is Iz. This path is Iz, and what goes here? This is IL. It goes through the load, right? Whatever goes here, it goes through the load. So this is Iz and this is IL. So this current is the sum of Iz and IL. So you can write IR is equal to Iz plus IL. Is it right? IR is equal to Iz plus IL. So that's what is given here. The total supply current means that is flowing through the supply, flowing through R1. That is the sum of Zener current Iz and load current IL. So you have to take care to make sure that the minimum Zener current is large enough to keep the diode in reverse breakdown. So there will be a minimum value of current, that should be there to keep the diode in its breakdown region. Otherwise, if it is not in its breakdown region, the voltage will not be constant, right? So that's why we have to make sure that the minimum current that is flowing through the diode is maintained, so that the diode is maintained in its reverse breakdown. So normally the value of that minimum current will be 5 milliamps for a Zener diode with a test current of 20 milliamps. With an IZT stands for test Zener current. So if the test current is 20 milliamps, then minimum Zener current you have to maintain is 5 milliamps. We will see this when you take some examples. So since load resistor RL and Zener diode are in parallel, so this Zener diode and resistance are in parallel, what is the voltage across the Zener diode? It is Vz. So that voltage is the same as the voltage across the load. What is the voltage across the load? That is V0. This output voltage is derived from Zener voltage. That means output voltage is equal to the Zener voltage, right? So instead of taking directly across the Zener diode, we have connected a load, but across the load, what is the voltage V0? That is the same as the breakdown voltage of the Zener diode. So V0 will remain constant even if Vin happens to change due to fluctuations in the AC line voltage. So this V0 will remain constant because that is measured across Zener diode. The breakdown voltage of Zener diode is constant. So V0 will remain constant even if Vin changes. That's the concept. So from the circuit, as I had said, IR is equal to IZ plus IL. IR is IZ plus IL. So if I rearrange this, IZ will be equal to IR minus IL. Now what is IR? From the circuit, IR is the current flowing through R1. So current flowing through R1 will be voltage drop across R1 divided by resistance R1. What is the voltage drop across R1? Voltage drop across R1 can be calculated by voltage at this point to the minus voltage at this particular point. What is the voltage at this point? It is Vin, right? The voltage at this point is Vin. And what is the voltage here? The voltage here is Vz. From here to ground, it is Vz. It is the same as V0 and Vz, right? It is the same. So voltage across R1 will be Vin minus V0. Voltage across R1 is Vin minus V0, or you can also write it as Vin minus Vz or Vin minus V0. And the resistance value is R1. That's why what is the current? Vin minus V0 divided by R1, right? Vin minus V0 divided by R1. That is the current through R1. You can call it IR, that is Vin minus V0 divided by R1. Now, if I substitute this value of IR in this equation, in place of IR, if I write this, IZ will be equal to Vin minus V0 divided by R1. In place of IR, I have written this, Vin minus V0 divided by R1 minus IL, that remains as it is, minus I. Okay. Now, let us assume, so we have considered that the input is unregulated. That means it is varying, it is changing. So let us assume that the changes in the input voltage is in between two values, that is Vin min and Vin max. It is varying between two values, Vin min and Vin max, that is maximum and minimum levels in between two values. And IL also varies between two values, IL min and IL max. IL min and IL max. So what we find is the minimum Zener current flows when the input voltage is minimum and the load current is maximum. Do you agree with this? See, what we mean by this is the total current entering is equal to the sum of this current and this current, right? So then if IL is minimum, IZ will be maximum, and if IL is maximum, IL will be minimum. Do you agree with this? For example, if IR, say if it is 10 milliamps, okay, if the current IR is 10 milliamps, then if you take IL as maximum value, if I take this as 9 milliamps, what will be IZ? It will be minimum, that is 1, because total of this and this will be 10. It is constant, right? So if the total is a same value, then if I take maximum value for IL, then I should take minimum value for IZ. If I take minimum value for IL, if I take IL is 0, then IZ has to be maximum. IZ has to be 10, so that IL is 0. And if IL is maximum, if IL is 10, then IZ has to be 0, right? But it cannot be 0 because you have to maintain a minimum current of 5 milliamps. So I just took an example that if IL is maximum, then IZ will be minimum, and if IL is minimum, IZ will be maximum. And in this equation, this is the equation that we have. So here, for minimum value of IZ, Vin has to be minimum and IL has to be maximum. And for maximum value of IZ, Vin has to be maximum and IL has to be minimum, right? So that's the concept we are saying. So if Vin varies between minimum and maximum values, Vin min and Vin max, and IL varies between minimum and maximum values, that is IL min and IL max, then we find that minimum Zener current flows when Vin is its minimum and IL is its maximum value. That means the current through the Zener diode must be more than that minimum value. Must be more than that minimum value Iz min, where that Iz min is the minimum Zener current required to keep the diode in its breakdown region. So this is that expression, V in min minus 0 divided by R1 minus IL max. This value has to be greater than this Iz min. So this value has to be greater than the minimum value. So this is the expression we have. V in min minus V0 divided by R1 minus IL max. This should be greater than Iz min. So then also the maximum Zener current flows. Maximum Zener current flows when V in is equal to V in max and IL is its minimum value, as I have shown you in the diagram. The V in has to be maximum and IL has to be minimum when the Zener current has to be maximum. So the current to the Zener diode must be less than that maximum value, okay, so that it is in the safe operation region. So this current, you know, if you put that in place of V in as V in max and in place of IL as IL min, right, then this has to be lesser than Iz max. This has to be lesser than Iz max for the safe operation, right? So these are the equations. This is about the Zener diode as a voltage regulator. We have seen it can be used without a load or with a load. Normally we use it with a load, and we have seen what are the equations of them. What is the equation for the currents, and in case of Zener diode with a load, we have seen the relation of when there can be minimum value of Zener current and when there can be maximum value. So in the next class we will solve some numerical examples of this. So it will be more clear when you solve numerical examples on finding values of different currents and voltages, and also sometimes you might also be asked to design a particular Zener diode voltage regulator for a specified voltage level, right? So I will take that up in the next class.